Today we're going to find the measures of angles formed by chords, tangents, and secants, and then we're going to determine the lengths of segments that are also created by intersecting chords, tangents, and secants. Now I know that you don't know what a secant is. We're going to get to that in a minute. Angles formed by intersecting lines have a special relationship to the related arcs formed when the lines intersect a circle. So when the two lines intersect, they're going to create two sets of arcs, and we're going to work with those. The relationship is slightly altered when the lines intersect inside or outside the circle. So the first one we're going to deal with, or the first theorem we're going to deal with, is the measure of an angle formed by two lines that intersect inside a circle, right here, is half the sum, so we're actually going to add the intercepted arcs. So if I look at my diagram here, the measure of angle 1 is actually going to be half the sum of the arcs that make the angle 1. So I've got arc x right here, and I've got arc y. And so the measure of angle 1 is going to be half of x plus y, or we can rewrite this as x plus y over 2. The second situation is going to be when the two lines intersect outside the circle. And so in the diagram, we've got three different possibilities. You have a line, or you have two lines that intersect the circle at two specific points. You have one of these lines that intersects the circle at 2 points, and then another line that looks like a tangent. This is a tangent line. This is a tangent. And then you have two tangent lines. But the way that you find the measure of the angle, angle 1, is actually going to be the same in each case. So the measure of the angle formed when the two lines intersect outside the circle is half the difference. So instead of it being an addition problem, this time it's going to be a subtraction problem. So we're going to subtract. And so the measure of angle 1 will be half of x minus y, or we can rewrite it as x minus y divided by 2. And if we just, before we move on, just talk about this first case right here, where you have two sets of lines that are intersecting the circles at 2 points, that actually has a very specific name. Any line that's going to intersect the circle at 2 points is called a secant. So a secant is a line that intersects the circle at two specific points. So if I look at my circle O, then I know that line AB is a secant because it intersects the circle right here, and it also intersects it right here. But let's actually do some problems with it. So the first example says, what is the value of each variable? And so this is really just going to be an application of some algebra. We just need to pay attention to which case we're actually working with. In part A, I have this angle x, which is what I want, and I looked that the two chords are actually going to be intersecting inside the circle. So I'm going to apply the first case. So I know that the measure of angle x is actually going to be equal to the two arcs that make it, the 46 plus the 90, and we're going to take that and we're going to divide it by 2. So if we just start doing some algebra, if I take 46 plus 90, that means that x will be equal to 136 divided by 2, which is actually going to be equal to 68 degrees. If we wanted to take a look at example B, now they're telling me what the measure of the arc, the angle is, but I want to figure out one of the arcs. But it is made by two lines that intersect outside the circle. So this is an outside situation. Since the measure of the angle is 20 degrees, I can set it equal to the relationship. So I know that 20 degrees is equal to, we'll always take the larger arc, which is going to be the 95, and we're going to subtract the smaller arc, and we're going to divide it by 2. We're still just going to do some straight up algebra with it, so I'm going to multiply by 2 on both sides to cancel out the 2. And you'll get 40 equals 95 minus z. I'll subtract 95 on both sides. And you get negative 55 equals negative z. And since you have a negative on both sides, you can cancel that out, and you can say that z equals 55 degrees. So you have 3 examples underneath that in your notes. Why don't you go ahead and try those, and I will fill them out as you do it. Okay. So for the first one, we want to know y. or W, I'm sorry, we want to know W, and I know that the measure of the angle is 70 degrees, and it's made by two lines that intersect outside the circle, so I'm going to set it equal to the difference. So 70 is equal to W minus 110 divided by 2. We'll do some math. We'll get 40 equals W minus 110, and you get W equals 250 degrees. Let's try it again. For part B, I know that this is an intersection outside the circle, and I want to know the measure of angle Y, and this is the angle I want. So I know that Y is equal to 110, because we're going to take this larger angle, or the larger arc, and subtract the smaller arc, and we're going to divide by 2. So when we do some arithmetic, I get 80 divided by 2, which makes Y 40 degrees. And then the last one, this is an intersection of the two chords that are inside the circle. So instead of it being a difference, I'm going to take a sum. And I know that the angle that we would be figuring out is 35. So it's 35 equals x plus 30 degrees all over 2. We'll multiply by 2 on both sides, and I'll get 70 equals x plus 30. We'll subtract x, or we'll subtract 30, and we'll get x equals 40. That's pretty much all that we have to do with angles. That's pretty much setting it up. Now let's take a look at an application. So if I have a satellite that is in a geostationary orbit, which means it doesn't really move, its altitude doesn't change above Earth's equator, and it has a viewing angle of Earth formed by two tangents to the equator. The view angle is about 17.5 degrees. What is the measure of the arc of the Earth that is viewed from the satellite? So I know that this is the angle that I'm given. What I don't know is I don't have a naming system for these two arcs. So why don't I just say the angle that I want is going to be, or the arc that I want is going to be x. So I can call arc AB x. And now I want to talk about arc AEB in reference to the whole circle. Well, if this starting arc is x, well, the rest of the circle has to be 360 degrees minus x. So arc AEB is equal to 360 minus x, and this was actually equal to x. And now what I can do is I can use that relationship that I had before, and we can solve for x. So I know that 17.5 is equal to the difference of the larger arc subtracting the smaller arc. So you get 360 minus x minus another x. So it's AEB minus AB over 2. We'll multiply both sides by 2, and we'll get 35. And we'll combine the terms on the top and get 360 minus 2x. I'll get, by subtracting negative 360 from 35, I'll have negative 2x equals negative 325. And dividing by 2, or negative 2 on both sides, I'm left with x is equal to 162.5. Let's try just another one very quickly. So a departing space probe sends back a picture of Earth as it crosses Earth's equator. The angle formed by the two tangents to the equator is 20 degrees. What is the measure of the arc, of the arc of the equator that is visible to the space probe? This is actually a very similar question to the last one that we did. Instead of the angle being 17.5 degrees, we're actually just going to replace it with 20. So I know that inside this point right here will be 20 degrees. I'm still going to use the naming convention. So if I call this A, B down here, and I can just pick a point on the major arc and call it E, I can still call this X, and I can still call this 360 minus X, and I'll actually just solve the problem the same exact way. So I know that it's 20 equals 360 minus x minus another x over 2. You'll have 40 equals 360 minus 2x, which means you get negative 2x equals negative 320. And x is actually going to be equal to 160 degrees. That's pretty much all that we can do when we're talking about angles angles that are made by intersecting lines in a circle. You really just have to pay attention to the situation and recognize whether it's a sum or a difference. You're also always going to be subtracting the smaller arc from the larger arc in the instance that you're going to be subtracting. Let's talk about lengths of segments. So these are three very special cases. You're going to have to learn how to recognize the three different ones. But there is a special relationship between two intersecting chords, two intersecting secants, or a secant that intersects a tangent, and it'll allow you to find the lengths of unknown portions of a segment. So here are the three cases. So case one is when you have two chords, and that'll be the product of the chord segments, and they will always be equal to each other. So if I look up here, I'll have A times B will be equal to C times D. The second case will be when you have two secants intersecting. So these are two secants that intersect, and it'll always be the products of the secants and their outer segments will always be equal. So if I take the length of the whole secant, which will be x plus w, and this length will be z plus y, I'll multiply that with the outer segments, and that will be, those two products will be equal to each other. And then the third one is when you have a secant and a tangent, where you take the length of the whole secant, so z plus y again, you multiply it times the outer segment, and you set it equal to this tangent squared. So we're going to square this. You really just have to learn to recognize when for what situation you've given. There is no easy way to remember all three cases. You're just going to have to study them. So if we want to find the value of the variable in each case, and I'm running short on time, I should have only about enough time to do maybe two of these. If we look, this is going to be a situation where we have two secants, so that's going to be case 2. And so what I know is that the length of the secant times its outer segment, when I multiply those, they'll be equal to each other. So essentially what I get is this. I know that the outer segment of the top one, which will be 6, times 6 plus 8 will be equal to the outer segment of the bottom secant, which would be 7, times the length of the whole thing, which will be 7 plus y. When I do some algebra and some arithmetic and I move some stuff around, this is what I'm going to get. I get the 6 times 14 equals 49 plus 7y. Six times 14 is actually 84. 49 plus 7y. And now all I have to do is just solve for y. So I'll subtract 49 on both sides, and you'll get 35 equals 7y, which means that y in this case is going to be equal to 5. Let's take a look at this last one for part B. This is actually going to be a case 3 situation because you have a secant and a tangent line. So I know that if I take the outer secant, the whole thing, so I'll have 16 plus 8, and I'll multiply it times its outer segment, and I'll set it equal to z squared, because it's the tangent line squared. You add 16 and 8 together, which will be 24. That's set equal to z squared, which you get 192 equals z squared, and that's going to be equal to 13.9. And so z equals 13.9. I'm just about out of time for this video. I really need you to go back and watch this video probably 2 more times just to make sure that you're getting everything. And I want you to try the next 2 on your own. They should be a case 2 situation and a case 1. For part A, you should get 13.75, and m should be 3